This is a model to demonstrate the effect aliasing can have on the closed-loop performance of a system. We've modeled a simple motor, a unity gain model, potentiometer output, an AC noise component, perfect sine wave of noise coupling into the output. So we've got the measured shaft position. We're modeling a sample rate here, sampling frequency of F sample, analog to digital converter, not modeled, but just represented graphically into the digital realm. So we've got sampled position, negative feedback, desired position, error, simple proportional gain of 1. Again, just a graphic here to represent digital to analog conversion back out to the amplifier. And again, our motor model. So we're interested in the frequency effects, but we'll look at a couple of things from our model. It's slow and given the parameter selection, but let's look here. A couple of numbers that are interesting, or a few numbers. Unity gain crossover around 0.1 hertz or 0.8 radians per second. The gain at 21 hertz, we're going to be interested in that, is well out 130 radians per second. It's off the chart, so it's 100 dB down, or a factor, 1 e to the minus 5 when you look at that as a ratio. Gain at 1 hertz, another number we're going to be interested in. That's about 6 radians per second. We're down 30 dB or 0.03. So we're going to inject some noise at 21 hertz. So this could be a 21 hertz sine wave, this F noise. And we're going to look at two sample frequencies, 50 hertz and 10 hertz. So let's start by looking at 50 hertz. So the top graph, we're just leaving from 0 initial condition to a reference, a desired position of 0.1 radian. Again, amplitudes don't much matter, and nor does the performance settling time performance of the controller so much. We're looking at in the bottom on a tighter time scale so we can see it, is the red sine wave is the 21 hertz noise component, and the green is as sampled. So at 50 hertz, we're sampling 21 hertz of noise, at least faithfully enough to acquire it at that frequency. And again, on a wider time scale, that is represented in the feedback error in red. And if we look, we have none of that red ripple to speak of on our output from our plant. And this is a very large noise amplitude. We're 2 radians peak to peak, the way we're looking at it, and our set point's only 0.1. So it's a ridiculous amount of noise, but it's intending to show the effect. If we were to look back at our gain estimates, this would coincide with this peak to peak here would be indicative of what we expect at that 21 hertz, or we were 100 dB down. So that's our very little noise coupling into our output because of the amount of attenuation we get from the plant, from the motor at 21 hertz. So because it's AC coupled into the output, we're effectively, our motor's just averaging that out. It doesn't even appear to affect our performance much. Now, obviously, if we're at a DC bias to it, or a slowly varying component, that would be another matter. But this perfect noise model, perfect sinusoid, we're relatively insensitive to it at that frequency when we sample at 50 hertz. So let's look at 10 hertz and see what happens. So let's sample at 10 hertz, and let's take a look at what happens now. So now we see something really strange. We have the same 21 hertz noise component. The only thing that's changed is our sampler is operating at 10 hertz now. 10 hertz. Everything else is the same. and we look here, we've ended up with this 1 hertz component. If you look at the time scale down here, that's 1 second, 14.5 to 15.5. So we've got a 1 hertz component down here, and that green is that's P sampled. P sampled doesn't, well, once it's at steady state, I mean, P sample will get that green will be the sum component on whatever the actual error is. So that 1 hertz, as far as the noise is concerned, that's the only thing that's on P sample. P sample starts life on the first iteration when the reference signal is applied. It has an error of 0.1, and it's just summing this 1 hertz component on that offset. And as we settle out, basically that's all we see is the 1 hertz component. If we look at the amplitude here, this is going to be representative of what we'd expect at that 1 hertz. We were what, 30 dB down, so 0.03. So if we were to look at the plant gain at 1 hertz, we are attenuating this error signal through the motor, but because it's a relatively low frequency, it's coupling into the output quite severely. And again, that 1 hertz doesn't exist in the quote-unquote real world. It's solely a result of this sampling having violated the Nyquist criterion. So we've sampled too low for a frequency component that's on the input line to our analog to digital converter, and we have folded a frequency. We have folded that frequency, in this example, down to 1 hertz, where we are indeed sensitive. Our plant will track that disturbance quite well, at least compared to the 21 hertz when we sampled at 50 hertz, if you'll recall. So this demonstration for control purposes is perhaps more useful than even the wagon wheel example of aliasing and some other things we look at in the signal processing realm to understand aliasing. Here we see the severe effect it can have in a feedback system if we are not filtering out components that are over half of our sampling rate. Again, we would need a low pass filter here of 5 to eliminate it. We don't have frequency components there, so we wouldn't actually need that filter. What we'd actually do is just sample at a higher rate, 50 hertz, 100 hertz, and then we'd have an easier job of designing an anti-aliasing analog filter on the input to the sampler. And that is the remedy in all cases, is right here in the analog domain, there needs to be a low-pass filter. A perfect filter would have a cutoff frequency, of course, no greater than f sample over 2. We would want to destroy all signal above f sample over 2. Now, there's no such thing as a perfect filter. There'll always be some noise, some frequency component on this line that we are going to sample. And so there's always going to be some degree of aliasing, but we seek to drive it to such a small effect, maybe relative to the resolution of our converter or other factors in our design that we're generally insensitive to it. But in the case of this demo, this model is certainly not insensitive to it. it violated the sampling criteria relative to this very severe noise condition and mapped it down to a frequency that is well near the bandwidth of our system, and we really see it coupling through to the output in a manner that it just simply does not at the 50 hertz, which of course does not violate the sampling criterion and Nyquist criterion because it's over twice the maximum frequency component on that input line, and that component happens to be this 21 hertz.